Hello. In today's video, we are going to talk about nanomaterials. This is the last topic in chapter 12. So nanomaterials, my favorite subject by far. So let's look at these. I think they're a lot of fun. I hope you guys do too. So to be a nanomaterial, to be a nanostructure, we have to have a particle that has at least one dimension on the nanometer scale. So to be on the nanometer scale, we have to be 1 to 100 nanometers. Right, so 1 to 100 nanometers. And remember, most substances have 3 dimensions, right? Length, width, the height. Not saying that all of them are, squares, but we generally think about length, width, height when we think about these 3 dimensions. At least one of them has to be on the nanometer scale in order to be a nanomaterial. We're going to look at today semiconductors on the nanometer scale, or on the nanoscale. There's going to be all 3 dimensions on the nanoscale. There are semiconductors on the nanoscale that aren't all 3 dimensions on the nanoscale, but the ones we're going to look at today, which are called quantum dots, are. And then we have nanometals, which again, the ones we're looking at, all 3 dimensions on the nanoscale. And then nanostructures of carbon. And only carbon. And these are between 1 dimension to 3 dimensions. On the nanoscale. So we're going to look at a couple different nanostructures of carbon. And there's going to be this 1 dimension in the nanoscale, 2 dimensions in the nanoscale, 3 dimensions in the nanoscale, so on and so forth. Okay, nanostructures, nano semiconductors, which I'm going to call quantum dots, are going to be very small. So these are going to be 1 to 10 nanometers in size. I think they're very interesting. They are used, they emit light upon excitation. Usually excite them using light at a different wavelength, and because of their emission properties, they are used in things like TVs and biological imaging. So if you've seen the Q dot TV, that's quantum dots that they're talking about. Quantum dots emit light well because of something called quantum confinement. And quantum confinement comes about because of the small size. I'll talk about that in just a little bit. And again, because of this small size, there are very few atoms in these structures. We're looking at like hundreds to tens of thousands. Of atoms. So basically taking an extended structure and truncating it, making it smaller. So let's look at what I mean with this quantum confinement. And actually, let's. So as I said, quantum confinement is due to the small size, the very few atoms. So with our fewer atoms means fewer orbitals. In the last video, when we talked about covalent network solids, we talked about these structures that have multiple atoms, and we get these huge valence and conduction bands, and we compared it to discrete molecules where we have single orbitals. With quantum confinement, we're somewhere in between. So we have a more discrete nature to our orbitals. Now, this is not discrete molecules. We still have hundreds to tens of thousands of atoms whose orbitals are overlapping, but we still don't have quite the same bands that we get. So we're somewhere in between a band and a discrete orbital with our quantum dots. And when we get that, when we have these fewer atoms, fewer orbitals overlapping, we have a larger band gap than the bulk semiconductor. So with quantum dots, we take a semiconductor, what we were looking at in the covalent network solids video / semiconductors video. So we start out with an intrinsic semiconductor, and then we take that semiconductor and we take it from the bulk scale into the nanometer scale, and that causes a widening of that band gap. Okay, so takeaway from this is, as we get smaller in size, our band gaps gets larger. Okay, so we would say that band gap and size are going to be inversely proportional. Okay, so as we get smaller, band gap gets larger. Okay. So for instance, and I don't know if I really noted this, these quantum dots are generally spherical in nature. Not quite spherical, they have some facets about them, but generally spherical in nature. So that's why we talk about radius. Okay, so they're inversely proportional. So for example, a common quantum dot material is cadselenide, and it has a bulk band gap of 1.85 electron volts. Okay, so that means if we have a crystal of cadmium selenide, it will have a band gap of 1.85. 6 nanometer cadmium selenide, so it has a diameter of 6 nanometers. It has a band gap of approximately 2.1 electron volts. Let's try another one. If we have a 2 nanometer cadselenide, hopefully you guys expect it to get even larger. And it does. It has a band gap of approximately 4.1 electron volts. So as we go from our bulk to smaller and smaller, that band gap gets larger and larger. Okay, so we don't do a lot of, I wanted to share this. This is kind of what's going on. We have our bulk semiconductor all the way to the left, so over here. As we decrease in our nanoparticle side or nanocrystal side, we get almost an amount of discreting about our orbitals, and that widens as we get smaller and smaller in size until we get to approximately a molecule size where we have legitimate discrete orbitals. So this is what's going on with our band gap. Okay, so with our quantum dots, we're going to do a couple of calculations. Really, we'll only do calculation of one thing with quantum dots. So when we think about a quantum dot, when they absorb light, they emit light. So and QD is quantum dots. So when it absorbs light, it emits light based upon the size of its band gap. So a larger band gap is going to have the emission of light that is more red, and then as we get a smaller and smaller nanoparticle, we are going to shift to higher energy. So we're going to blue shift our emission. Okay, so this would be the largest with a red emission, and then the smallest with a purple emission. Remember, we go from red to orange to green to blue to violet within our color spectrum. This is going to be lowest energy at red, and then highest energy at purple. Okay, so highest energy, more blue shifted, lower energy, more red shifted. Okay, so I will expect you guys to be able to calculate the energy of emitted light. And it's simple, you're just going to use E equals HC lambda. So I want you to be able to do calculations between energy and wavelength, basically for your nanomaterials, or for your nanoquantum dots. Okay, we also want to look at, here they are in color. So these are our smallest ones over on this side, our larger ones over on this side. As we change our size of our nanomaterial, we change our band gap size. Okay. Okay. Let's look at nanometals now. So nanometals are very small crystals of metals, or metal crystals. So these are going to be, again, spherical. So spherical. Generally. Not always, but generally. And they're going to be between 1 and 100 nanometers. Okay. So, again, we're going to get different properties than we see in the bulk. So, with our nano semiconductors, we get a change in the emitted light. With our nanometals, the color that the material is different. So they are colored, so they're not metallic looking anymore. So right here, these are some nanometals right here between 5 and 90 nanometers in size, and they change in color. Okay, they don't emit light like a nanoparticle does, or nano semiconductor does, but they're colored, and the color depends on the size. Oh, also this is nano gold. Generally, we're looking at noble metals when we're looking at these nanometals. stuff like nano gold, nano silver, nano platinum, those type of things. So when we take our noble metals, they're going to become reactive at this size. Okay. And the other difference between a nanometal and bulk metal is we have lower melting points for a really small one, so between or lower than 20 nanometers generally. Last thing we want to look at is nanostructures of carbon. So nanocarbon in comparison to bulk. So bulk, we have 2 allotropes of carbon. That's going to be diamond and graphite. Okay. With nanocarbon, we have a lot, but we're going to look at C60, which is also called Buckminster fullerene. Or short name, buckyball. Then there are carbon nanotubes. And graphene. This first picture, this is C60. It looks like a ball, right? So it's going to be all 3 dimensions on the nanoscale. And it literally has 60 atoms of carbon in a ball. Because it is so small, it will dissolve in solvents. Which, as we know, diamond and graphite do not do. And it is a very interesting species. It absorbs most of the solar spectrum. So they use it or they're trying to utilize it in electronic devices and stuff like that. There are other variants, not necessarily all of them are C60. There's like C20, C72, so different size balls with different amounts of carbon. This was discovered in 1985, and I meant to put that up there. By Smalley and Croto and what was the other gentleman's name? And Curl. So Smalley, Curl, and Croto were the 3 gentlemen who actually got a Nobel Prize for C60 back in, well, they discovered it in 1985. They got it somewhere in the 90s probably. Our next one we want to look at is a carbon nanotube. So it is a tube of carbon. This was discovered in 1992. Okay. So this is going to have 2 dimensions. On the nanoscale. The length itself, the length of the tube, will not be on the nanoscale. Okay. So this can be made semiconducting or metallic, or can have semiconductor or metallic properties without dopants. And it is also the strongest one-dimensional material out there. And that one-dimensional is a dimension that is not on the nanoscale. Right? So the two dimensions that are on the nanoscale, they kind of consider that to be zero-dimensional when we're thinking about bulk-type properties like tensile strength, which is what we're looking at when we're talking about a carbon nanotube. Carbon nanotubes are added to a lot of things to increase strength, including bikes, because it's very lightweight, but it adds an incredibly large amount of strength to it. Then we have graphene, which is a sheet of graphite, basically. So to get graphene, they isolated it from graphite using a piece of tape. So it was first exfoliated in 2004. Okay, so they knew about graphene prior to this because they understood the structure of graphite, but they were actually able to get single layers of graphite, which are called graphene. Okay. It was isolated with tape. So they took a piece of tape, got a piece of graphene. It is going to be one dimension on the nanoscale. And because it has one dimension on the nanoscale, it is the thinnest two-dimensional structure. Again, the structure that's on the nanoscale is not considered as a dimension because it's so small. It has the highest tensile strength for two-dimensional structure, or it has a, let's just go with high tensile strength. It also has a high electrical conductivity. And it is considered a semi-metal because of that high electrical conductivity. Okay. That is all the things I want you guys to know about nanomaterials. Hope you guys found it as interesting as I do. See you guys later. Bye.